Welcome to Mech Cosmos, Engineering, Explained. In the first half of the 20th century, the battleship was the most powerful weapon system ever built by human beings. A single ship could destroy an entire city from 40 kilometers away. Its guns fired shells weighing over a ton at targets completely invisible to the naked eye. Its armor was so thick that ordinary shells simply bounced off its sides. It required a crew of over 2,500 men to operate, and it represented the absolute peak of a nation's industrial, military, and engineering capability. To build a battleship was to demonstrate to the entire world that your nation had mastered the highest levels of steel production, precision engineering, naval architecture, and industrial organization. The battleship dominated naval warfare for nearly a century. From the Dreadnought Revolution of 1906 through 2 world wars, it defined how navies fought each other, how wars were won and lost at sea, and how great powers projected military force across the oceans of the world. Nations measured their power and prestige in battleships. Treaties were negotiated to limit their numbers. Enormous national resources were devoted to building them. And then in the space of just a few terrible years in the early 1940s, the battleship was rendered completely obsolete by a weapon it had never been designed to face: the aircraft carrier and the naval aircraft. Today we explain everything: how a battleship's main guns worked, how the shells were loaded and fired, how the fire control systems calculated solutions for targets 40 kilometers away using mechanical analog computers, how the armor was designed and why it worked against some threats but not others, how the propulsion system drove 7,000 tons of steel at over 50 kilometers per hour, how the crew of 2,500 men operated this extraordinary machine, and why the most powerful surface warships ever built were made irrelevant almost overnight by the advance of aviation technology. We are Mech Cosmos, Engineering, Explained. Let us begin. The defining feature of the battleship was its main battery, the large caliber guns that gave it its devastating firepower and that distinguished it from all other warship types. The size of a battleship's guns determined its fighting power and its place in the hierarchy of naval vessels. The largest battleships ever built, the Japanese Yamato and her sister ship Musashi, carried 9 460mm guns arranged in 3 triple turrets. Each gun barrel was 21 meters long, longer than many houses. Each shell weighed 1,460 kilograms, more than a family car. The guns could fire these enormous projectiles to a maximum range of approximately 42 kilometers. The muzzle velocity, the speed at which the shell left the barrel, was approximately 780 meters per second. The shells traveled in a high, arcing ballistic trajectory, reaching altitudes of several thousand meters at the apex of their flight before descending steeply onto the target. The propellant that fired these enormous shells was not contained in a single cartridge as in a rifle or pistol. The shell and propellant were loaded separately. The propellant consisted of multiple bags of powder, typically 6 bags for the Yamato's 460mm guns, each containing a measured quantity of a specialized, smokeless propellant. After the shell was rammed into the breech of the gun, the propellant bags were loaded one by one behind it. The breech was then closed, and the gun fired electrically. The quantity of propellant used could be varied, using fewer bags, reduced muzzle velocity and range, allowing the guns to engage closer targets without the shells flying over them. Using all bags achieved maximum range. This variable charge system gave the gun crew flexibility in engaging targets at different distances. The turrets that housed the main guns were extraordinary engineering structures in themselves. Each triple turret on the Yamato weighed approximately 2730 tons, heavier than many destroyers. The turret sat on a barbette, a massive cylindrical armored structure extending downward through multiple decks to the magazines deep in the hull where the shells and propellant were stored. The turret could rotate a full 360 degrees on precision roller bearings to engage targets in any direction. The gun barrels could be elevated from near horizontal to approximately 45 degrees. The elevation that provides maximum range for a given muzzle velocity. The entire loading and ramming mechanism that lifted shells from the hoists, raised the propellant bags and rammed them into the breech, was powered by hydraulic and electric systems. Despite the enormous size and weight of the shells and propellant, the loading system could achieve a sustained rate of fire of approximately 1.5 rounds per gun per minute. The fire control system that directed these guns at targets 40 kilometers away was one of the most sophisticated and complex systems ever built, using purely mechanical and electromechanical technology. The fundamental mathematical problem of naval gunnery at long range is formidable. The target is moving, typically at speeds of 20 to 30 knots. The firing ship is also moving. The shell takes 60 to 90 seconds to travel 40 kilometers. In that time, a ship moving at 30 knots will have traveled approximately 1,500 meters from where it was when the gun was fired. The fire control system must accurately predict where the target will be when the shell arrives and direct the guns to that predicted future position. It must account for the target's current course and speed, the firing ship's own course and speed, wind speed, and direction, the air temperature and density at the altitudes the shell will pass through, the rotation of the Earth, and the known ballistic characteristics of the specific shell and propellant combination being used. The primary sensor for the fire control system was the optical rangefinder. The Yamato carried a main rangefinder with a baseline, the distance between the two observation points, of 15 meters. This enormous baseline gave the rangefinder extraordinary accuracy at long ranges. Trained operators peered through the eyepieces and adjusted the instrument until the two half images of the target coincided, giving a precise measurement of the target's range. Additional observers tracked the target's bearing. The range and bearing measurements were taken continuously as the ships maneuvered and fed into the fire control computer. The fire control computer was a masterpiece of mechanical engineering, a machine of extraordinary complexity built entirely from gears, cams, levers, and precision mechanical components. It had no electronic components and no digital processing, yet it continuously integrated the range and bearing measurements from the rangefinders, calculated the target's course and speed by tracking the changes in these measurements over time, projected the target's future position, accounted for all the environmental and ballistic variables, and output the required gun elevation and bearing to place the shell on the predicted target position. This output was transmitted electrically to indicators in the gun turrets, which the turret crews used to train and elevate the guns. The entire system required teams of highly trained operators working in coordination to produce accurate fire. In action, the fire control spaces deep in the ship were among the most intense and demanding working environments imaginable. The armor of a battleship was its second defining characteristic. It was the feature that distinguished a battleship from all other warship types, and that justified its enormous cost and complexity. The Yamato's belt armor, the vertical armor protecting the sides of the ship at the waterline, was 410 millimeters thick at its maximum. This was not simple mild steel plate. It was specially manufactured face-hardened cemented armor. Steel that had undergone a complex heat treatment process to create an extremely hard outer face layer that would shatter an incoming armor-piercing shell on contact, combined with a tougher, more ductile inner layer that would absorb and contain the fragments. The combination was far more effective against armor-piercing shells than a simple plate of equal weight. The deck armor protecting against plunging shells, shells arriving at a steep angle after a long flight, and against bombs dropped from aircraft was up to 230 millimeters thick on the Yamato. The turret faces, the surfaces directly facing the enemy, were the most heavily armored parts of the ship at 650 millimeters thick. The turret sides and roofs were somewhat thinner. The barbettes protecting the ammunition hoists between the turret and the magazine were also heavily armored. The conning tower from which the ship would be commanded in action had walls 500 millimeters thick. The entire armor arrangement was designed around the concept of the zone of immunity, a range band at which the ship's armor could defeat enemy shell fire. At very short ranges below approximately 20 kilometers, shells arrived on a relatively flat trajectory and struck the belt armor at angles close to perpendicular. The belt was thick enough to stop them. At very long ranges above approximately 30 kilometers, shells arrived on a steep plunging trajectory and struck the deck armor nearly vertically. The deck was thick enough to stop those. Within the zone of immunity between these two ranges, the belt was too oblique to the incoming shell for penetration, and the deck was too steeply angled to be penetrated either. Outside this zone, the ship was potentially vulnerable, but then the enemy would be facing the same problem in reverse. The tactical implication was that battleship engagements were most dangerous at very close or very long range, and safest at intermediate distances. The propulsion of the Yamato was an engineering achievement that matched the scale of everything else about the ship. 12 compound boilers burned oil to produce steam at high temperature and pressure. This steam drove 4 sets of geared steam turbines arranged in 4 engine rooms. The total shaft horsepower output was 15,300, approximately 14,000 kilowatts. This drove 4 propeller shafts, each fitted with a 4-bladed propeller 6 meters in diameter. Despite displacing 700 to 800 tons at full load, making her one of the heaviest ships ever built, the Yamato could reach a maximum speed of 27.5 knots, approximately 51 kilometers per hour. Sustaining this speed required consuming approximately 600 tons of oil per day. The ship carried approximately 6,300 tons of fuel, giving her a range of approximately 7,200 nautical miles at 16 knots. The boiler rooms and engine rooms occupied a very large portion of the ship's internal volume and required over 300 engineering personnel to operate and maintain at sea. The conditions in the boiler rooms were extremely demanding. Intense heat noise, and the constant physical demands of monitoring and adjusting the boilers and their numerous auxiliary systems. The engineering department's skill in maintaining the propulsion plant determined the ship's speed and maneuverability, critical factors in surviving enemy fire and maintaining tactical positioning. The crew of the Yamato numbered approximately 2,500 officers and men. They lived, worked, and fought within the steel hull through long patrols and in battle. The crew was organized into specialized departments, each responsible for a critical aspect of the ship's operation. The gunnery department operated and maintained the main battery secondary guns and anti-aircraft weapons, as well as the complex fire control systems. The engineering department kept the boilers, turbines, and all auxiliary machinery operating. The navigation department conned the ship and maintained its position in formation. The damage control department was responsible for detecting and responding to battle damage, flooding fires, and structural damage to keep the ship fighting. In action, each man had a precise station and duty, and the coordinated performance of the entire crew determined whether the ship survived. The secondary armament of the Yamato provided defense against smaller surface ships and increasingly important anti-aircraft protection. She carried 12 155mm guns in 4 triple turrets for surface engagements and extensive anti-aircraft batteries that were progressively expanded as the threat from aircraft became increasingly apparent. By 1944, she carried 24 127mm dual-purpose guns and over 150 smaller-caliber anti-aircraft weapons of 25mm caliber. Despite this formidable volume of fire, the anti-aircraft defense proved insufficient against organized air attacks by large numbers of aircraft. The fundamental problem was that the anti-aircraft guns of the era, optically aimed and mechanically fuse-set, could not reliably engage fast-maneuvering aircraft at altitude in sufficient numbers to break up a determined attack. The end of the Battleship Era came with brutal speed. On December 10, 1941, 3 days after Pearl Harbor, the British capital ships HMS Prince of Wales and HMS Repulse were attacked and sunk by Japanese land-based torpedo bombers and dive bombers off Malaya. Both ships were underway and maneuvering and had their full anti-aircraft batteries in action. They were sunk within 2 hours. It was the first time that modern capital ships had been sunk solely by air attack while underway and able to maneuver freely. The message was unmistakable to naval officers who understood its implications. Battleships without air cover were fatally vulnerable to air attack. The Yamato herself was sent on a one-way mission on April 6, 1945. With Japan facing inevitable defeat and the American invasion of Okinawa underway, she was dispatched with only enough fuel for a one-way voyage. There was insufficient fuel in Japan for a return journey. Her mission was to beach herself at Okinawa and fight as a fixed gun battery until destroyed. She never reached her destination. On April 7th, she was located by American carrier aircraft and attacked by waves of planes. Approximately 280 aircraft in 10 successive attack waves. She was struck by at least 11 torpedoes and 6 bombs over the course of 2 hours. The torpedo hits on her port side caused severe flooding that the damage control teams could not control. She developed a fatal list, capsized, and exploded as her magazines detonated. She sank in approximately 400 meters of water, taking over 3,000 of her crew with her. American losses in the attack were 10 aircraft and 12 airmen. The most powerful battleship ever built was destroyed without firing her main guns at a single enemy ship. The battleship was not defeated by a better battleship. It was defeated by an entirely new concept of naval warfare in which the decisive weapon was not the gun, but the aircraft operating from a ship hundreds of kilometers away. The aircraft carrier could strike at ranges completely beyond the reach of any gun. It could attack from directions and altitudes that the battleship's fire control systems were not designed to engage effectively. The battleship's carefully designed zone of immunity was meaningless against an enemy that never came within gun range. The entire rationale for the battleship's existence, its ability to destroy enemy ships with gunfire, was rendered irrelevant by an adversary that could kill it from 200 kilometers away without ever being threatened in return. That is how a battleship worked, and that is why it no longer exists. We are Mech Cosmos. Engineering. Explained. If this video gave you a new appreciation for the most powerful surface warships ever built, and the extraordinary engineering that went into them, then subscribe, hit the notification bell, and join us for the next video. Because every machine has a story, and we are here to tell it.